Have you ever looked at your clothes and just wondered, how do they get the color to stay so bright? Well, today we're going to pull back the curtain and dive into the amazing chemistry that makes colors stick around for good. I mean, it's a story we all know, right? You get a brand new, super vibrant t-shirt, and after just a few washes, it's a sad, faded version of its old self. But then you've got other clothes that seem to last forever. What's the deal? It's not magic. It's actually some seriously clever chemistry. And the secret is all about a special kind of dye. The hero of our story today is a class of molecules called reactive dyes. And you gotta think of these less like a paint that just sits on the surface and more like a chemical superglue that literally fuses the color to the fabric, making it a permanent part of the material itself. So how does this superglue actually work? Well, a lot of other dyes just kind of cling to the fibers with a pretty weak attraction. But a reactive dye? It forms something called a covalent bond. We're not just talking about sticking to the fiber here. This is a full-on chemical reaction where the dye and the fiber actually share electrons and become one single unified molecule. It latches on and absolutely refuses to let go. And the design of these little dye molecules is just brilliantly simple. You can think of it like a custom-built tool that has three main parts, and each part has a very, very specific job to do. So first up, you've got D, the chromophore. This is the part of the molecule that actually makes the color we see. It works by absorbing certain wavelengths of light and reflecting others back to our eyes. This is the source of that beautiful blue or that vibrant red. Then, right in the middle, you have X, which is the bridge. Its job is pretty straightforward, but absolutely essential. It's the connector piece, holding the color part and the action part of the molecule together. And that brings us to the magic ingredient Y, the reactive group. This is the real business end of the dye. It's an active chemical hook that's been specifically designed to go out and hunt for a partner on the fabric's fibers, like the cellulose and cotton, and lock in that permanent bond. So, what's the end result of this whole reaction? Well, the dye and the fiber literally become a single, new, larger molecule. The color isn't just sitting on the fabric anymore. It has become a fundamental part of the fabric. And here's where it gets really cool. Chemists don't just have one type of hook. They have a whole toolbox full of them. They've designed all these different reactive groups like triazine and pyrimidine groups, and each one has slightly different properties. This variety is so important because it lets dyers match the perfect dye to the right fabric to get the best possible results. Okay, so we have this amazing molecule, but how do you actually get that hook to connect with the fabric in a giant real-world dye bath? It's not as simple as just throwing everything in a pot. Nope, it's a very carefully controlled three-step process. The whole dyeing process really breaks down into these three stages. First, you've got absorption. This is where we have to convince the dye molecules to get out of the water and get up close and personal with the fabric. Next is fixation. And this is the magic moment where we actually trigger the chemical reaction that forges that permanent bond. And finally, there's the wash-off, which is a super important cleanup step to get rid of any unbonded dye, leaving you with that perfect, long-lasting color. You can almost think of this as a chemical recipe. In that first phase, which is often called exhaustion, you add salt to the dye bath. What the salt does is it essentially pushes the dye molecules out of the water and encourages them to get cozy with the fabric fibers. But at this point, they're just kind of resting there. To kick off the fixation phase, an alkali, like soda ash, is added. This completely changes the chemistry of the bath. It activates the dye's hook, and it forces it to form that permanent covalent bond. But, this whole process isn't quite as straightforward as it sounds. There's a catch. That little reactive hook on the dye molecule is so eager to bond with something that it creates this dramatic race against a very unlikely competitor. So what's the biggest threat? You might think it's another chemical or maybe a problem with the fabric. But no, the dye's number one enemy is the very water it's dissolved in. This is a process called hydrolysis. See, if that reactive hook on the dye bumps into a water molecule before it can find a spot on a fiber, it'll just react with the water instead. And once that happens, the hook is used up. That dye molecule is now totally inert and useless. Its color that can no longer stick to anything. And this is a huge deal. Depending on the conditions, a massive amount of dye, we're talking anywhere from 10 to a whopping 60%, can be lost to hydrolysis. That's just wasted dye, it's wasted money, and it creates all this colored wastewater that then has to be treated. So, managing this race against water is really the key to efficient dyeing. And chemists have figured out how to do this by creating different types of dyes that work best under different conditions. We can basically group them into two main categories.
This gives us two main game plans. On one side, you have your cold brand dyes. Their hooks are super reactive, they're ready to bond at the drop of a hat, even at lower temperatures. On the other side, you have hot brand dyes. Their hooks are a bit more stable, a little less reactive, so they need a big push from high heat to really kick them into action and form that bond.
And here's a look at what a real-world recipe for one of those hot brand dyes looks like. It's this carefully controlled dance of time and temperature. You can see how the salt is added in stages to gently coax the dye toward the fabric. And it's only at the very end that the soda ash is added, and the temperature gets cranked all the way up to 90 degrees Celsius to force that final permanent bond. It really is all about perfect timing. So when you step back and look at the whole picture, it's pretty clear why these dyes totally dominate the industry. They dissolve easily in water. They form those incredibly strong bonds that give them excellent fastness. That just means the color doesn't fade or rub off. Plus, they're relatively cheap to make, and they come in just about every color you can imagine. So, the next time you pull on your favorite, super colorful shirt, you can appreciate the incredible chemistry that's at work. It's not just color sitting on the surface, it's color that's become a fundamental part of the fabric. The secret, as you know now, is all in that permanent chemical bond. Kind of makes you look at your closet a little differently, doesn't it?